Hi everyone, today we're going to have a look at counting techniques. So this is chapter 8.5. In the last few videos we've had a look at finding probabilities. So the probability of A we found by the fundamental rule that it's going to be the number of events where A occurs out of the total number of outcomes. So if we had a dice and we're looking at um, how many times a 1 shows up, or we might be looking at even numbers. So let's say even numbers, well, there's three different ways we can get that, a 2, a 4, or a 6, over the total number of outcomes, which would be 6. So 1, 2, 3, 4, 5, 6. So that's what we've had a look at as a fundamental rule for probabilities. So the number of elements in both A and the sample space need to be able to be counted and um, used with this formula. So we're going to now consider two counting techniques. Um, One where the order is important, and one where the order is not important. And we can write these as so an order is the same as a arrangement. Okay, so I might be arranging um, the dice in uh, from smallest to largest.
McKaylee Bell, can you come to the bus area, please? McKaylee Bell to the bus area.
The other option is, or the other way it's written is what's called a permutation. And that's what we're going to be using as a definition. So when we see the word permutation, it's going to be the order. Now the option where the order is not important is just a selection. Okay, so this is just a selection. And we write this as a combination. Okay, so order is not important, so we're not worried about the order that they come out in. Okay, so let's say we've got three people. So person A, B, and C. And I'm going to arrange them. I'm going to pick two of the people out and stand them next to each other. And I'm interested in how many different combinations can I put them together. So person A, B, and C. So I'm going to select two and I'm going to stand them next to each other. So I'm interested, how many different ways can I put them? So first one is A and B next to each other. Another might be when B and C are next to each other. And I need to work out how many different ways I can do that. Sometimes it's not so easy, especially with large samples, but for three, it's relatively straightforward. So A and B, so just do it systematically, A and B, or A and C. A and, B and C. Okay, or B and A. So note that those two are different. AB is different to the arrangement of BA. I can also have CA, again, different to that one. AC is different to CA, and also CB, and same thing. So in total, there's 1, 2, 3, 4, 5, 6 different ways I can arrange these three people. Okay, this is a lengthy process, especially when we have lots of people, for example. So we might have D, E, F, and G. Okay, and the more we have, the more combinations we're going to have, and it's going to be a lot more complicated. So we need a easier way or something that we can use quicker to be able to list out or work out the possible arrangements. So for this example, we can use a box table. And what we're doing is in this first box, I'm going to determine how many different ways can I put one person in here. So I've got 3 people. Okay, either A, B, or C could go in that first one. So I'd put 3 there. In this next one here, however, I've already selected one person. So they're already in that first one, which means there's only 2 possible selections I can have depending on what we've got on the first one. So if A is in there, so let's say we've put A in this first one, well then only B and C could go in this second one. If B was in there, only A and C, and then if C was in there, only A and B. So there's only 2 different ways, doesn't matter which one I put in first. So it's 3 and 2. And this is handy because we can use these. Once we've filled out our box, we basically just multiply each of the numbers. So 3 and 2. So 3 times 2 will give us 6, which is what we worked out before. 1, 2, 3, 4, 5, 6. So this is an illustration of the multiplication principle. So we're going to look at that in a moment. Multiplication principle. Okay, so the multiplication principle, basically if we have m ways of doing one procedure, and for each of those there are n ways of doing the second procedure, then we can say there are m times n ways of doing the first and second procedure. So let's expand on our example before. Let's use a different color. So let's say we've got person A, B, C, and D now. And I want to work out how many ways I can arrange them. Well, using our box, there are 4 different ways I can select the first person, which means there's going to be 3 different ways of selecting the second person. So the number of ways I can arrange them is going to be 4 times 3. So I have 12 different ways of arranging them. So I can expand on that even further if I was interested in looking at how many ways I can order 3 different people. So the first one is 4. Okay, I can select one of the 4 people from the start. I'm going to be left with 3 to choose from in the next one, and then 2 for the one after there. So it's 4 times 3 times 2. And 4 times 3 is 12 times 2. We get 24 different ways of ordering them. So as you can see, this number gets quite large depending on how many ways we want to arrange them. Now, I'm not going to write out 24 different ways because that will take so long, which is why these box tables are quite useful. And as a final statement, if I was interested in the total number of arrangements of either 2 or 3, so total arrangements of either 2 or 3 people, then it would be 12 plus 24, which gives me 36. So this illustrates the addition principle. So having a look at worked example 10, We've got a 5 digits, 2, 6, 7, 8, and 9. And we're going to assume that there's no repetition of the digits in any one number. So only one number can occur. So part A, how many 3-digit numbers can be formed? So 3-digit numbers. So how many 3-digit numbers can I form? So that's where we use our box table. So we want 3 different uh, numbers, sorry, 3-digit numbers. In my first box, I've got 1, 2, 3, 4, 5 to select from. Then I would have 4, and then I would be left with 3. So it's going to be 5 times 4 times 3, which will be 60. So there are 60 different ways I can form a 3-digit number from these 5, assuming that I can't repeat the same number. So I couldn't have 5, 5, and 6. Okay, so I can't have that. How many numbers with at least 4 digits? At least 4 digits. Okay, at least 4 digits. Okay, I'd be looking at least 4. So there's that one. There's also the possibility of 5 digits. And then we can only have 5. So for 4 digits, I've got 1, 2, 3, 4, 5 times 4 times 3 times 2. And for this one, 5, 4, 3, 2, and 1. Okay, so I'm going to work them out and then add them up, add the totals. So 5, 4, 3, and 2 will give me 120 different ways, 120 different ways. So 120 plus 120 gives me 240 different possibilities of having at least 4 digits. And the third question, how many 5-digit odd numbers? 5-digit odd numbers. Okay, this is interesting because we have to go backwards because we're only interested in the 5. Well, actually, we'll start with 5 boxes, but we're only interested in the odd numbers. So 1, 2. So there's only 2 different ways I can do that. So once the last digit has been formed, there's going to be 4 choices for the first digit. Okay, if I select 7, there's only 4 different selections I can do for the first one, which means there's only 3 for the second, 2 for the first, and 1 for the last one there. So a bit strange. We'll have 4 times 3 times 2 times 1 times 2. And we can say there's 48 odd 5-digit numbers. And the last one of the 5-digit numbers is chosen at random. So 5-digit number chosen at random. We want to find the probability it will be an odd number. Okay, so we're looking at from part B, one of the 5-digit numbers. We found was 120. Okay, there's 120 different ways I can put a 5-digit number. And I'm going to say let A be the event, the 5-digit number is odd. So we can say the number of A, the event A, so the number of 5-digit numbers that are odd was 48. So that means finding the probability of A, so probability that the 5-digit number is odd, is simply going to be 48 out of the total of 120, because we're just interested in the 5-digit numbers. We're assuming that we've already been given a number which is a 5 digits. We're just interested in whether or not it's odd. And if we simplify that down, we find that it's 2/5. So as you've probably noticed, there's a bit of a pattern happening with our boxes. So if we have 4 selections, so A, B, C, and D, arranging them in 4 different ways, it was 4, 3, 2, and 1. So as you can see, we're going down by 1 every time. Okay, a bit of a pattern happening, which means this is what's called factorial notation. You might have come across this before. So factorial notation is the number of ways of arranging n objects, n objects in a row. So it is n, and we use this explanation mark, meaning factorial, is going to be the number, the original number, multiplied the original number minus 1, multiplied by the original number minus 2, times by the original number minus 3, and this continues until we go down 2 and 1. So for this one here, our original number, there was 4 in total, so we're looking at 4 factorial. So it was 4 times the next one, n, 4 take 1 gave us 3, and then 4 take 2 was the 2, n take 3, okay, well, it's just 2 and 1. We always have 2 and 1 at the end. So it's 2 and 1. Okay, so 4 times 3 times 2 times 1 is what we had. So that's factorial notation. Just as an extension on this factorial notation, we've been having a look at combinations in a row, so row arrangements. We're just going to have a quick look at what happens when it's not in a row. So we're looking at what happens when it's in a circle. So I've got A, C, and B. So I'm interested what happens when it's in a circular arrangement, not in a row. And really, if I had A, B, and C, for a row, it would be 3 factorial, okay, which is 6 combinations. 3 times 2 times 1 gives me 6. But as a circular arrangement, there's only 2 ways I can do this. Starting at A, it's A, B, and then C. So going clockwise. Okay, A, B, and then C. However, if I go if I went anti-clockwise, it's A, B, or C. And clockwise would be A, and then C, and then B. So A, C, and B. So there's only really 2 different ways that I can do that. and that would be similar for um, larger numbers as well. If we had A, B, C, and D, etc. So n factorial is the number of ways arrange n objects in a row. However, n minus 1 factorial is the number of ways of arranging n objects in a circle. Okay, n take 1 factorial. So this one I had 3 different um, A, B, or C. So it would be 3 take 1 factorial, which is 2 factorial. It's just simply 2, which is what we had, 1 and 2. So that's in a circle. So slightly different. So in a row, it's just the n factorial, n take 1 factorial for circles. So moving on to worked example 11, we've got 7 students in a queue in a straight line at a canteen. And we're interested in how many different ways can the queue be formed. So I might have students A, B, C, D, etc. And I'm interested in how many ways I can arrange them. So obviously it's not practical to draw out all the different arrangements, as we'll find out shortly. Now it's in a straight line, which means we're going to use our n factorial equals n times n take 1 times that pattern continues times 2 times 1. Okay, we've got 7 students, so we're going to have 7 factorial different ways of arranging them. So 7 times 6 times 5 times 4, 3, 2, 1. And if I work that out, I'll find that it is 5,040. So there are 5,040 different ways in which the students can be arranged. So it's quite a lot, and as I said, we wouldn't be able to practically draw out that every time. Just as a quick little note, instead of working out a very long string of numbers like 7 factorial, I could write this as 7 times 6 times 5 factorial. Sometimes we're interested in simplifying it. So 5 factorial, well, that's just 5 times 4 times 3 times 2 times 1 anyway. So I could be interested in 7 times 6 times 5 factorial, just something quicker to write. So that's just, that'll come up shortly. The second part of the question, we're interested now at their seating arrangement. So they all buy a drink at the canteen and they find a table. It's a circular table and they all sit around it. So we've got a table and there's 7 seats. And how many different ways can I arrange the students? So it's not practical to draw out the situation. So we're just going to use our formula. So for circular arrangements, it's n minus 1 factorial. In this case, we've got 7 students, so 7 take 1 factorial. So it's going to be 6 factorial. So 6 factorial is just going to be 6 times 5 times 4, 3, 2, 1. And if we do that, we should find that it is 720 different ways that we can seat students around the circular table. Third part of the question, this group of students have been shortlisted for maths, history and art prizes, and we're finding the probability that one person in the group receives all 3. So we've got 3 prizes, and each prize can be awarded to any one of the 7 students. So it might be handy to draw our table. For the first prize, we've got 7 students can be awarded that first one, but we also can have 7 students be awarded the second one. Okay, doesn't matter if they double up, and there could be 7 ways that they can receive the third prize. So the number of ways the prizes can be awarded is going to be 7 times 7 times 7. I'm going to let A be the event that the same student receives all 3 prizes. And there are 7 choices for that student. Okay, there's 7 students, and I'm interested in if one of those students gets all 3 prizes. So there's 7 ways I can have that happen. So finding the probability that A occurs, the probability that the event is the same for the 3 prizes is going to be the number of students, so there's 7, out of the number of ways that I can select that, which we found out is 7 times 7 times 7. So it's 7 over 7, 7, 7. I can do some simplifying. It's 1 out of 49. So the probability that one student receives all 3 prizes is 1 out of 49. So I'm just going to leave the video here. We're going to do part 2 in the next video. So stay tuned.